We've already seen the angular momentum for a single particle moving in space. If we have a rigid body, so we have some extended object that is rotating together, then we can think of this object as a bunch of individual pieces, and as the object rotates, each individual piece has a little velocity, and each little piece is going to have a corresponding momentum. And so we could calculate the momentum for each piece, but that gets very complicated. It goes beyond the scope of this class. The point is that if the object rotates on a fixed axis, so we have some sort of axle or something holding it in place, forcing it to rotate about a specific axis, or if it is rotating about an axis of symmetry, then for that limited case, that kind of special case, we can say that the angular momentum is going to be I times omega, where I here is the moment of inertia about the given axis, and omega here is the angular velocity. If we look in the picture, we can see the same thing, that the angular velocity vector is going to point along the axis. It's pointing along the axis such that if you are looking from that direction, it appears as if the object is rotating counterclockwise. That's how we're defining positive rotation, is that the angular velocity vector is pointing, it does point along the axis, and we're looking at the object along that axis as if the angular velocity vector is pointing at us. And so the angular momentum vector would be proportional to the angular velocity. And this shouldn't be surprising as well. This relationship that we're talking about here directly parallels linear momentum. If the object is rotating about some other axis, or it's free to rotate about some arbitrary axis, then the angular momentum can be a pretty complicated function. But for these two cases, we can find the angular momentum for a rigid object pretty easily.